So, welcome, guys. We want to start our next lesson. It's called Multiplication on the Complex Plane. Multiplication on the complex plane. So, we want to see geometrically what multiplication does when you do it on the complex plane. Now, before we start, we want to talk about a property of the absolute value of a complex number or the modulus of a complex number. And that property is this: the modulus of the product of two complex numbers. So PQ. Now remember, P is like an X plus YI and Q is like a plus BI. They're complex numbers here. So the modulus, or the absolute value of the product, is equal to the product of the absolute values. All right? And for complex numbers, this is a true statement. And what we essentially want to do is explore this statement and prove that it is true. Okay? Now, the other thing that we want to do is we want to look at regular old multiplication of complex numbers. And when you multiply this out, you get AC plus ADI plus BCI plus BDI squared. And I squared being -1 then leads to the real part being AC minus BD, and the imaginary part being AD plus BC times I. And so whenever you multiply two complex numbers, the answer takes this form. Now, it turns out that when you multiply complex numbers, you could, if you look at it, you could just have two real numbers multiplied together if B and D were 0. Or you could have a real number times an imaginary number if C was 0 and B was 0. Or you could have an imaginary number times an imaginary number if the A and C were 0. Or you could have a whole complex number times a real number, a whole complex number times an imaginary number, and a complex number times a complex number. So in other words, there are 6 cases, and we want to explore these 6 cases geometrically as well as algebraically to see what happens to multiplication on the complex plane. All right? And we want to verify that in each case this property will hold. The modulus of a product is equal to the product of the moduli. All right? So let's look at a couple of cases right now, a couple of simple ones. So case number 1, a real number times a real number. What happens on the complex plane when you multiply? Well, if you take 2 plus 0i times 3 plus 0i, that's going to multiply to give you just 6 plus 0i. 2 plus 3 is 6, right? And in fact, on the complex plane, if we look at that, here is the complex number 2, 0. And then here is the complex number 3, 0. And if you multiply those, you essentially stay on the x-axis. So geometrically, multiplying these complex numbers will stay on the x-axis. And if you look at the moduli, all right, the modulus of 2 plus 0i is equal to the square root of 2 squared plus 0 squared, or just 2, right? Square root of 2 squared is just 2. the modulus of 3 plus 0i is equal to the square root of 3 squared plus 0 squared, or just 3. And the modulus of the product, 2 plus 0i times 3 plus 0i, is equal to the modulus of just 6 plus 0i, which is the square root of 6 squared plus 0 squared, or just 6. And so what we see here when we look at this is that our property will hold, all right? The property being the product of the modulus of the product is equal to the product of the moduli. And so we see that 6 is equal to 2 times 3. All right? And geometrically, we see when we multiply real numbers, they just stay on the x-axis. All right? You could look at this as a doubling of the 3 or a tripling of the 2, either way. All right? So now let's go to the next case. A real number times an imaginary number. So what we want to do in looking at this second case, real number times imaginary number, all right, is we just want to look at the simplest example. So we're going to take 1 plus 0i, and we're going to multiply it times 0 plus 1i. So the real number is 1, the imaginary number is 1i, or just I. And what happened when you multiply that, that's easy to see that it's just 1i. But what happens geometrically? What's going on here? So if we look at this, and we take the real number right here, 1, 0, if we multiply it by an imaginary number, in this case 1i, we end up moving the number, the result is going to be on the complex line. Now, this is going to be true even if I took like 2 times 3i, right? So if you take 2, 0, right, and you multiply times 3i, that is 6i, and it moves up, but it ends up on the complex number. So that's when you have a real number times an imaginary number, it ends up on the imaginary line. So if you remember what happened last time, if we multiply real numbers times real numbers, we stay on the x-axis. But if we multiply real numbers by imaginary numbers, we go to the y-axis. For instance, if I take negative 1, 0 and multiply that times I, that will also go to negative I, right? Negative 1 times I is negative I. But all the results end up being on the y-axis. And so geometrically, a real number times an imaginary number is always an imaginary number. In other words, the real number just becomes a scalar multiple, a doubler or a tripler, etc., of whatever the complex number is. And so another way to think of it is it rotates those real numbers in the counterclockwise direction 90 degrees. All right? And I'll leave it up to you to just go ahead and check, does our property still hold for this example? All right, I don't want to necessarily show you all of these, but if you take 1 times I, you get I. So the modulus of I is 0 plus 1 squared, which is 1. And the modulus of P is 1, and the modulus of Q is also 1. So 1 times 1 is equal to 1. So the property holds for our original example. Okay? So let's go to case 3, which would then be, well, what would happen if you had an imaginary times an imaginary number? What would happen in this case? And so in this case, because an imaginary, an I times an I is equal to I squared, since you're going to get an I times an I, even in an example like 2I times 3I, you get 6I squared. Since you're always going to get an I squared, we know I squared is -1. And so we can see what's going to happen geometrically. We're going to start off with I, but then we're going to still rotate 90 degrees and end up with a real number. So we go from the y-axis to the x-axis in this case, but we're still rotating. And for instance, the 2i times the 3i, so there's 2i, and if I multiply it times 3i, I'm still rotating, I end up out here at -6, all right? And so it's still a rotation. So for case 2s and 3, those are both rotations of 90 degrees in the counterclockwise direction. Imaginary times an imaginary. And I leave it to you to prove for this example or this one that this statement holds true. Go ahead and try that on your own. So now we get to the more interesting cases. Let's look at case 4. This would be a real times a complex number. So in this case, we're looking at an example like 3 times 1 plus 2i. All right? So a fully complex number. What happens in this case? Well, if you look at the two numbers, the 3 or 3 plus 0i, geometrically, that is on this axis. There's 3, 0. All right? The 1 plus 2i, if you'll remember, is right here. And there's its modulus, the length, its absolute value. And so if we take 3 times 1 plus 2i, we get 3 plus 6i. So what does that become? Well, 3, 4, 5, 6. If you plot that point, it turns out that point ends up being on the same line, but it's just 3 times as far. So the geometric interpretation of a real times a complex number is essentially it's a dilation, right? It's just it just increases the number, but it keeps it in the same direction. Now, excuse me, this is very much like the real number times a real number. When we had 2 times 3, remember, we went from 3 and then we doubled it out to 6, right? And so a real number times a real number is a dilation in the same direction as all the real numbers, which is the x-axis, whereas a real times a complex is in the direction of the complex number, but it's a dilation in that direction, a scalar multiple, all right? Okay? And then the question then becomes, gosh, does this little property still hold? So we'll do it for this one. So we first want to find the modulus of p, which is 3 plus 0i. So 3 plus 0i, the modulus of that, is equal to the square root of 3 squared plus 0 squared, or just 3. And then the modulus of 1 plus 2i, the complex number, is the square root of 1 squared plus 2 squared, which is 1 plus 4, or the square root of 5. And then the modulus of the product, and the product in this case was 3 plus 6i, so its modulus will be the square root of 3 squared plus 6 squared, which is 9 plus 36, or the square root of 45. And 45 is 9 times 5, so this simplifies to 3 square root of 5. And if you look at it, if you multiply these two, 3 times square root of 5, you get the answer right there. That's pretty cool. So this property holds in this case, continues to hold. So we showing it for specific cases, not full proofs, but it's enough to give us a sense of what is going on. Okay? So then what happens if we multiply by a complex number? So let's take a peek at that. And that would be case 5. So case 5 is an imaginary number times a complex number. And a good example of that would be, let's go with 2i times 1 plus 3i. Okay? Like that. So what would happen here? Now, if you remember, when we multiplied by complex number, an imaginary number before, we ended up with a rotation. And so the question is it still going to rotate even though it's multiplying by a complex number? So let's take a look at that. So we're going to start off with 2i, all right, which is right here. And then we're going to start off with also 1 plus 3i, which is this number. So here's our two complex numbers, okay? Now we're going to take 2i times 1 plus 3i, and that gives us 2i plus 6i squared. The I squared is negative 1, so this becomes 2i minus 6, or negative 6 plus 2i. All right? And so if we look at that, negative 6 is in this direction. So let me shrink this. All right. And so we go 1, 2, 3, 4, 5, 6. And plus 2i, then that will go up. So we end up right here. And if you look at this, oh my gosh, we end up rotating this again 90 degrees in the counterclockwise direction. We also, of course, because of the 2, we expanded the size. So what does the I do? It ends up still rotating 90 degrees, all right? And so multiplying by an imaginary number rotates 90 degrees. Multiplying by real numbers dilates, all right? And so we see that what we see here are geometric transformations occurring. Geometric transformations, all right? And that's kind of an interesting thing. Let's go ahead and do the last case, a complex number times a complex number, all right? And so for case 6, which is complex times complex. Let's just grab an example. Now, I would think that it would rotate and dilate, but the question becomes, how much does it rotate? And so what we want to look at, let's do this example, negative 2 plus 3i times 1 plus I. There's two complex numbers, fairly simple. We can go ahead and multiply this out, so let's go ahead and do that. And then we'll look at it geometrically. So we get negative 2 minus 2i plus 3i plus 3i squared. The I squared is negative 1, so that's a minus 3. So we end up with negative 2 minus 3 is negative 5, and negative 2i plus 3i is plus I. So now let's look geometrically at what happened. All right. So our first number is 1 plus I. So let's mark that. That's right here. There we go. Okay. Our second number is the negative 2 plus 3i. So there's negative 2. There's the 3i. So that number is right here. And there's the modulus, the absolute value. And so now let's look at the product. The product is negative 5 plus I. So where's that going to be? So we go through negative 3, negative 4, negative 5 is out here. I is right there. So it's right there. And this is what it looks like. Now, it seems a little bit strange, but it turns out that this angle and this angle are the same. Or, excuse me, that's not correct. Let me undo that. I apologize. It turns out that this angle, let's call it alpha, and this angle to the second number we'll call beta. It turns out that if you measure the angle all the way around to the product result, that angle ends up being alpha plus beta. So this is equal to alpha right here. This part, this little part right here. But the whole angle is equal to alpha plus beta. It's this particular, so it's a rotation counterclockwise again, but it's this thing that's going to help us when we start to do the trig. And that's why we wanted to look geometrically at what happens, okay? Now, your job when you get to the assignments is to kind of figure out what happens. A couple of things that they do, they say, well, what if you multiply by I cubed as opposed to an I? What if you multiply by an I cubed? Well, all you have to remember is I cubed is negative I. So what does that do? It changes the coefficients and it rotates, all right? And so the question is, what direction is it going to rotate? And you can look at that geometrically and then describe it. Another problem, because this property, we did it for 3 of them, because this property holds, another type of problem that they do is they'll tell you that the product is 2 plus 6i, okay? So they say PQ equals 2 plus 6i. And then they'll say P is something like 2 plus 4i. So the question then becomes, they then go, what's Q? Or they'll say, what is the modulus of Q? So they ask questions like this: what are Q, or what is the modulus of Q? Well, if you know that P times Q is this and P is this, then you could say, whoops, so if you had P times Q divided by P, that gives you Q. So with division, you could answer this question. And so we would do 2 plus 6i divided by 2 plus 4i, which means we would go ahead and do the division, which means we would multiply by the conjugate, which would give us, in the numerator, 4 minus 8i plus 12i minus 24i squared. And in the denominator, we'd get 4 minus 16i squared. And then we would work that out. Minus 24i squared is plus 24. So we get 28 plus 4i. And the denominator would become 4 plus 16, or 20. So this is 28 over 20 plus 4i over 20, which we could simplify to 7/5 plus 1/5 I. And so this would be Q, all right? Now, the other thing they say, well, what's the modulus of Q? Well, since we know PQ and P, we could say, well, the modulus of PQ is the square root of 2 squared plus 6 squared. The modulus of P is the square root of 2 squared plus 4 squared. And then we do not know the modulus of Q. So that's our variable. And so we'd work this out. This is 4 plus 36, or the square root of 40, is equal to the square root of 4 plus 16 square root of 20 plus the modulus of Q. And this would be square root of 40 minus square root of 20. And the square root of 40 is actually 2 times the square root of 10. Is that right? 4 times 10. And subtract then 2 times the square root of 5, and that will equal the modulus of Q. So this would be your answer for the modulus of Q. Now, a question I have is, the Q that I found up above, will it give me this modulus? So let me check that out. So I would take the square root of 7/5 squared plus 1/5 squared. That's the modulus. And I would then work that out. This would be 49 over 25 plus 1 over 25, which would then be equal to the square root of 50 over 25, which is equal to the square root of 2. And now my question is this equal to this? And if we look at this up here, square root of 10 is actually square root of 2 times square root of 5. So we can say this is 2 times square root of 2 times the square root of 5 minus 2 times the square root of 5. And we can factor, take the 2 square root of 5 out, and we're left with square root of 2 minus 1. So that simplifies it a little bit, but I'm not sure if those are the same. They should be the same, and so I'm going to check it. You should check it too. I'm going to check it right now. The square root of 2 is equal to 1.41, and I'm going to do 2 square root of 10 minus 2 square root of 5. and they're not the same. So that leads me to maybe my division up above was not the correct approach to doing the problem. Even though it gave me a nicer answer for the modulus of Q. So we'll have to think about that one. That one's kind of strange. This is a whole new thing. I've never seen this before. And I am liable on occasion with new things to make mistakes, just like you. And so I'm just looking at this. Certainly for the modulus of Q, we did that in the correct... Oh, I know what I did. I put plus here. I wrote it wrong. It's times. So I did do it correctly. And this is correct as well. So what I really have here is the square root of 40 equals the square root of 20 times the modulus of Q. I ended up writing it with an addition. I apologize. Very sorry for that. Well, the square root of 40 divided by the square root of 20 is equal to the square root of 2. So if you were asked to find Q, you could then find the correct modulus. Or if you were asked to just directly find the modulus, you could do that as well. And both will lead to exactly the same answer. So I apologize for my error. But that's always something. I told you I'm liable to make a mistake. And what was my mistake? It was just a copy error. I just wrote down the formula wrong. And so those are things, this is why I say you always write the formulas, because you need practice. It helps you memorize them. Okay, so those are the kinds of problems that you're gonna deal with on this assignment. So that's all I have for you. Good luck. Make sure you go through the lesson and do the practice. It will be very helpful to you. And just so you can, I can't erase this right here. Oh, it's not erasing everything. There we go. So if I erase this right here, that doesn't look so bad. And we'll erase this right here. So now you can see the correct work. So I apologize again for that righto, not a typo, a righto. Good luck. Enjoy the assignment. Interesting little problems. Okay? Alrighty, bye. Whoops.